So, hi everyone. Welcome to the 2021 Stellar Society lecture here from Guilford Technical Community College. We're part of the North Carolina Science Festival. Festival's in its fourth week this year. There have been lots of cool events around the state, lots of them virtual like this one, some in person. We hope you've had a chance to check out some of those and to check out the remaining events for the rest of the month. Just use your favorite search engine and look for NC Science Festival, and you'll be able to link to a calendar and see all kinds of cool events for some homegrown science in North Carolina. I've got my official festival shirt on tonight. This particular lecture was going to be part of the North Carolina Science Festival last year, but with the eruption of COVID, a lot of events got canceled and postponed, and we weren't allowed to have this talk last year. This year's speaker was last year's speaker, and so she's happily we've got her back this time to have the talk. It's our 10th Stellar Society lecture. The Stellar Society is Guilford Tech's astronomy club, and they over the years have supported Klein Observatory through using some of their club funds and volunteering. And they came up with the idea that we should have this lecture every spring and bring in a big name or a regional name to give a talk. And we folded it into the North Carolina Science Festival around the same time because it got off the ground about a decade ago as well. And so it's been a nice partnership, and we're really excited about tonight's speaker, and we're glad she's here. We missed her last year. We had a nice session this afternoon with the Stellar Society club members hanging out, talking science with Dr. Cleaves. And based on that, I'm sure that you're going to enjoy tonight's talk. I'd also like to thank the Gtcc Foundation for helping make this possible. They support all of our events here, and it's the donations to the foundation for Klein Observatory programs that many of you maybe in the audience have made that make these kinds of events possible. So thanks to the foundation, and thanks to you for supporting the observatory. So we're excited tonight to have Dr. Ilse Cleaves from the University of Virginia to give the 2021 Stellar Society lecture. She is currently an assistant professor in the astronomy department at Charlottesville and the chemistry department. She also has an appointment there. And she's an adjunct scientist at the National Radio Astronomy Observatory, also in Charlottesville. So she seems to work everywhere up there. Before going there, she was a Hubble postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics. Her PhD came from the University of Michigan, where she did work similar to what she's going to be talking about now. And her undergrad degree in astrophysics is from Rice University. She's a rising star in astronomy. She's well decorated for the research that she's done. She received the Annie Jump Cannon Award of the American Astronomical Society, which is recognizes important work that young astronomers do. And she was awarded a Packard Fellowship in 2019. So let me turn things over to Dr. Cleaves. She's doing really exciting work figuring out how solar systems form and how planets form. So Dr. Cleaves, take over and welcome.
All right, great. Can you hear me?
Yep, we've got you.
All right, great. And thank you so much, everyone, for joining and for having me this evening. I'm sad that I can't be there in person, but I'm glad that I can reach you all, at least in this form here, now that we have so many wonderful digital platforms to connect with each other. I'm excited to tell you about, in this lecture, walking through our current understanding of the formation and the origins of planetary systems, both our own solar system, but also planets orbiting very different types of stars, distant stars, so-called exoplanets. And so this is a really exciting era for exoplanetary science. We're not only finding new exoplanets every single day, it seems, but we're also starting to learn a lot about them in detail. We're starting to learn a lot about their compositions and even the detailed compositions of their own atmospheres. So these are planets around distant stars that we've never traveled to, and yet we're learning so much about them and everything about their properties. And so this talk will be sort of a review of the origins of our current understanding of those compositions of these exoplanets and our solar system planets, and trying to do this by studying specifically how and where these compositions come from, by studying the environments that the planets are forming out of. We call these environments around young stars so-called protoplanetary disks. So you'll hear the word disks quite a lot in this talk. These are disks of material encircling very young stars in the first few million years of their lives, and they form the building blocks of that future generation of planets. This area of research, planet formation, is an incredibly rapidly growing field, especially in the last decade. New facilities, new observational facilities have been coming online and are soon coming online, hopefully later this year, that will shed brand new light on the planet formation process. And hopefully solve many of our questions, but also inevitably introduce many, many more. And so before digging into that, I want to just sort of introduce what we currently understand about planetary composition. And the first example of our current understanding and also our current lack of understanding is actually not that far from home. It's our own Earth. Earth, while we have an up-close and personal view of this planet, there's still tremendous open questions around the composition of Earth, both its solid rocky component, but also the liquid component. Where did the oceans come from, for example? We don't understand entirely why it has the carbon abundance it does. It's actually really lacking in carbon, even though it feels like carbon and carbon-based life is everywhere we look. It's actually a relatively carbon-poor rock. We don't entirely know what's even in the core of our Earth. What does it have? What does it have beyond the iron and nickel core that we know? There's something else hiding in there, something a bit lighter. And so there's a ton of questions surrounding just our own Earth, tons of puzzles that we have yet to really understand. Going a bit further, I think this is, yeah, there we go. Going a little bit further, just a step out from our Earth, we don't actually have to go outside of our own solar system to see the diversity of planets and moons and examples of the outcome of the planet formation process, showing us that so many different possibilities are out there. Jupiter, as just one example, it's mainly hydrogen and helium, like our sun. It has ammonia and water-rich clouds. It has a odd puzzle, though, with its oxygen abundance. The early Galileo probe seemed to suggest that the water abundance in the atmosphere of Jupiter was really low. And so Juno is going to shed light on this very soon and tell us sort of definitively what's going on with these other species like oxygen and the water and carbon as well in the atmosphere of Jupiter that look so strange. Other interesting puzzles here, Enceladus, one of my favorite moons, has an icy crust and a giant global subsurface ocean surrounding or engulfing a rocky core. And so from Enceladus, we can see plumes coming off, and we see water coming out of Enceladus via these plumes, and high temperature minerals that have been cooked at the base of these oceans. And so there's a lot of interesting puzzles there, and interesting to think about or speculate about what lies beneath in that deep subsurface ocean. Titan is a wonderful, really neat example. It's one of the future NASA targets via the Dragonfly mission. Titan is really a bizarre moon in that it's actually quite similar to our Earth. It's the only other body in our solar system with liquid surface oceans, although they're not made of water. They're more made of like a hydrocarbon soup because it's so cold that the water freezes into solid form. And so you have this amazing diversity even out of in the same planetary system that formed out of that same initial young protoplanetary disk of our sun. Going a step beyond our solar system, like I said, new exoplanets seem to be discovered every single day. There are examples of hazy, rocky water worlds that seem to be losing their atmosphere. Actually, a great example of atmospheric loss here is the case of WASP 121b, where the tail of atmospheric loss was seen as a shadow as the planet crossed the star. It had a sort of typical exoplanetary transit, except for the fact that it didn't stop. It had a long shadow, a long tail afterwards. There are planets around carbon-rich stars that have such high densities that if the planet itself had also inherited some of that carbon, the pressures would be so great. It was so nicknamed the diamond planet. This is 55 Cancri E. And so these are wildly different examples of exoplanets here that are not anything like what we have in our own solar system. In addition to these specific examples, we're also in this era of exoplanet statistics, and we're starting to learn about the diversity of architectures of these other planetary systems. One of the neat features that came out of the Kepler data set is that it seems like, at least it's not uncommon to have tightly packed systems of planets, tightly packed configurations, where when I animate this shortly, and I hope the audio doesn't play, we'll see soon, on top of the dashed lines here, which indicate the orbital positions of the planets in our solar system, overlaid are all of the known Kepler planets as of 10 years ago. So this is already in itself out of date, but it will already show you the amazing diversity that was seen even at that point of the diversity of architectures. These are little tiny planets whizzing around their surface, their host stars at a very close distance. There you see them going. I'll turn the audio down just in case. And it's going to zoom out here. So, our entire inner solar system is represented in the central region. And here you have systems where you have multiple gas giants orbiting well within the distance of our own planet Mercury's orbit. And so this is completely different from our picture and our understanding of our solar system, and sort of has thrown a wrench into our understanding of planet formation at large, which was mainly described or mainly designed to explain our solar system, and not this very, very bizarre set of exoplanets that are very tightly packed. All right, there we go. And in addition to that, we don't have to rely on such, these kinds of cartoons, these animations of orbital properties of exoplanets. This is a really nice time sequence data set of HR 8799, a 10 to 20 million year old planetary system where the planets are here, 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 and here. And when I hit play, you're going to get to see them move. And these are relatively massive, more than Jupiter mass or Jupiter mass-ish gas giant type planets that are young and self-luminous. And so they're still warm from their initial formation. There we go. I'll play it one more time. And you can see them orbiting their central star. It's pretty amazing. And there's a scale bar to show you. So 20 AU. The orbital distance of Pluto is something like 40 AU. So you have massive gas giant planets orbiting at distances that exceed even Pluto's orbital distance in our solar system. To me, the most amazing thing out of this data set was that because the planets B, C, D, and E were self-luminous, they all were able to have the light split into the corresponding spectra for each of these planets. And from each of these spectra, through detailed model fitting, the authors were able to derive the compositions of the molecules that made up the atmosphere, and also then extract interesting information like the carbon over oxygen ratio in the planet's atmosphere. And so we'll come back to this very important ratio in this talk later. So where does this this compositional diversity, this orbital diversity, where does it all come from? So if you look at our own solar system, you get your first clue. First off, if you look at the planets and the orbits, on the whole, they pretty much all fall into the same flat plane. Here you have Pluto, of course, the oddball, but for the most part, the planets, of the 8 planets of our solar system fill this plane. And so this is not a coincidence. This is a remnant of the original protoplanetary disk that formed our planetary system. The disk itself was just a natural part of the evolution of forming a star and planetary system in the first place. You have some initial molecular cloud that will gravitationally collapse. And with a little bit of spin, it will naturally set up a disk around a gravitationally dense object that's eventually going to form into your young protostar. It's getting fed through this early disk by material infalling from that remnant cloud. Once the infall or the feeding stops, you're left with a long-lived protoplanetary disk surrounding a mostly formed star, which has about 10, maybe 20 million years to assemble its planetary systems, at least its gas giants, before you have the sort of longer-lived planetary system. And this can, the evolution and formation can continue well on, hundreds of millions of years after the dispersal. You have lots of collisions of rocky bodies, but there's no more gas left. And so whatever Jupiters or whatever gas giants you form, that's what you've got to work with. And so if we look at one of these disks, the typical properties are that they're mainly molecular hydrogen, just like our sun. That's no coincidence. They have some amount of helium, and then everything else that makes up us and all of our planets and all of the sort of interesting things, including life, are fairly trace species. So the carbon, the oxygen, the nitrogen, and so forth. In the dusty component, the dust makes up about 1% of the mass of these disks, mostly in the form of gas. Just 1% is what makes up, things like our Earth, our silicate-rich Earth. These dust grains they do many things. They will change the physical and chemical properties of the disk, and if they get cold enough, they'll start to freeze, have ices freeze out and to form shells around them. So you form things like water and CO2, ammonia, formaldehyde. Lots of sort of simple ices like that will freeze out onto these cold dust grains. And so when I say cold, I mean something like 10 Kelvin, and warm in my book is something like 100 Kelvin, though I'm guessing that this may be cold for many of you across the board. And densities here, we're talking, a million parts per centimeter cubed up to sort of 10 to the 12 parts per centimeter cubed when you're really close to the star. Now, a question around protoplanetary disk science, a central question here is, how do we actually go about converting this nebulous gas and dust and ice-rich disk into a future planetary system? What is the machinery that takes us from point A to point B? There's certainly some clues already in our solar system. We see that the gas giants in the sun, they're samples of our nebular disk. They're mainly hydrogen and helium, just like the interstellar medium. This is what is left over of that gas-rich component. The terrestrial planets and the rocky asteroids, those are remnants of the solids of that dusty component that remains in the disk itself. Then you have your cometary bodies, the ice-rich bodies, and even the icy asteroids that tend to carry some of that volatile water, CO2, CO ice, and that very volatile material. The comets are this sort of more pristine record of that information. And within our solar system, there are even more interesting imprints. There's chemical fingerprints of how planet formation proceeded in our solar system. These are graphs showing you sort of the amount of carbon relative to silicon in different bodies of our solar system, and then over here is just nitrogen relative to silicon. And from this, there's imprints of the planet formation's effects. So you have the comets out here that are quite rich in their amounts of carbon and nitrogen. And if you trace this all the way back down here to the Earth, you have relatively little carbon, relatively little nitrogen. And Earth is also relatively carbon and nitrogen poor, even when compared to asteroids like Enceladus chondrites, some of the feeding asteroids that we think actually probably were some of the formation some of the building blocks that led up to the formation of Earth. And so there's a lot of information in here. And so we can use this and try to work backwards and understand sort of what happened here. But we're actually not just limited to studying our own solar system. There are tons of examples of star and planet formation ongoing today in the nearby actively star forming regions in our galaxy. Orion is one of the most striking, it's not the closest, but it's one of the most striking examples of star formation in action. This is a beautiful picture here from Hubble in the background. And then you see these little tiny squares, these postage stamp zoom-ins of little tiny stars that are in the act of forming their own planetary systems. And so you see there in this, this is a disk seen in shadow against a bright nebular background. So it looks like it's a dark lane because it's just blocking light from the background nebula. Then you have all these examples down here of disks that are sort of closer to the center of the action, and they're getting disrupted. They're in a bit of a race against time. You know, they want to form planets, yet they're also being kind of irradiated and destroyed by being in this sort of violent environment. We can study these disks at multiple wavelengths. This is another system, HK tau, A and B, a binary system. Here you see the star and the disk in scattered light or direct light up here. Here is the same system seen in millimeter emission. So this is thermally glowing dust grains, roughly a millimeter in size. And so what you're seeing here is now the glowing warm pebbles that are making up future planets. Over here, this is the gas orbiting the star, and the color coding is showing you gas that is either moving away from you, which is red shifted, or blue moving towards you, which is blue shifted. So you're seeing the rotation of the disk and its orbit around the star. And then, of course, with enough creativity, you can create an artistic representation here of such a system. And so these different wavelengths uncover different parts of the process of how these disks are assembled and how they're assembling future planets. Now, observing disks in general is a challenging feat. So here to scale, so here's the moon, and this little tiny circle, this little tiny dot represents roughly the size of a typical disk. And so I don't want you to get ill, so I'm gonna hit play, hopefully this works. So we're zooming in now, zooming across the face of the moon to get a closer picture, a clearer picture of the typical size of a protoplanetary disk. There it is. You can even see the pixels in the moon. And for scale, I've given some of the sizes of the resolution of previous telescopes, particularly those in the sub-millimeter, which is what I'll talk about shortly, is one of the best wavelengths to observe such disks. Previous generation single dish telescopes did not have the resolution to really see much detail, such much fine-grained structure, because the resolution element was often much larger than even the biggest disks we can observe in the sky. And so the picture of planet formation, our first picture of planet formation was made in 1987, shown here. This is T-Tau, T-Tauri. It's now like the namesake of all disk system, what we call this entire class of systems, typical of astronomers to do that. And here you have the red shifted and the blue shifted emission, so coming towards you and going away from you, so you see the rotating disk. First observations of a rotating gas disk. Then here, from another protoplanetary disk system, this one's in Taurus. This was an interesting case. The star has moved over, it should be right there. But here you have a trace species, an isotope. And so this became one of the first tracers of sort of looking at isotopic chemistry in disks. And this is one of the interesting ways in which we want to connect our solar system and its interesting isotopic ratios to these environments by studying their isotopic ratios and looking for matches or discrepancies. Hubble, of course, came in and took those gorgeous images. So this is one of the early images from 1995 of an edge-on disk. It looks a lot like a flying saucer when viewed from the side, and you have this dark smudge across the sky. You can see the star peeking up here and more brightly shining here. And so what you're seeing here is the pancake disk, but just viewed from the edge-on configuration, the side configuration. So we're not able to directly see the light from the star, we're just seeing it glance off the surface on the upper and lower side. And so this gave really unprecedented resolution and gave us a lot of information on the sort of thickness and the structure. But unfortunately, because of the density of those tiny little dust particles that fill the disk, we didn't have a ton of information about what was going on in the heart of the disk, especially where we think the planets are forming right in there. And so this is why radio wavelength light is so such a wonderful tool. The beauty of radio wavelength light is that, well, we're limited by those early low resolution telescopes with a single dish. We can instead use a combination of multiple telescopes in a process known as interferometry to try and actually make equivalently the image that a larger telescope would make by spreading out lots of smaller telescopes over a large area. And so we can basically achieve the resolution of this sort of fictionally large telescope through a system of much smaller, much more efficient and affordable telescopes. So we can get Hubble-like resolution, HST-like resolution, by just separating your telescopes out by kilometers in distance. And so this acts like a larger single telescope. And so this is one of the first observations, the Plateau de Bure. And so here you see from this was an observation of gas, and it was sort of forming this ring-like structure, but still it was a pretty messy system, right? We're seeing, there's a ring of gas. And this was interesting because it showed us that disks are highly structured. There seems to be something sculpting the gas, perhaps. And so led to some interesting theories about companions or planets. Now we have many more examples in the last 20 years. So this is the catalog of circumstellar disks. You can go to it down here. There's the link. There are over 250 disks that have been resolved. There are many, many more, hundreds, if not even at this point, thousands of known protoplanetary disks. But in terms of disks where we have images, there are over 250 examples, and they're constantly being updated, here. But really, this era of imaging planet formation and action was completely turned on its head in the last decade by the arrival of the Atacama Large Millimeter / Submillimeter Array, or ALMA for short. It's in the Atacama Desert. It's an incredibly high-end dry site. Nothing beats it. It's 5,000 meters elevation, and it provides an incredible window, an incredible picture of the submillimeter, millimeter sort of wavelength sky. To give you an idea of what an incredible technology feat this is before we get into the data, here is a picture of a good friend and collaborator, Ruud Visser, who was the astronomer on duty. He tweeted this here of him at the high site with the ALMA telescopes. And here, for scale, I've now used Ruud, who he's himself a very tall Dutch man. But here you can see that the dishes are rather extended. So you have now over six and a half roughly roods across, 12 meters in more formal units. And the telescopes themselves are spread out over a very large area, up to 16-kilometer baselines across. And the amazing thing about that is it gives us that spatial resolution to act like Hubble, or even better than Hubble resolution. The neat thing about it is that these connection points are all roads. It's a completely configurable system, and so you have these transporters that can move the telescopes around and shift our picture. And so here is an example of the improvement in the data. I think the picture shifted, so apologies for that. But here you have the original observations of TW Hydra and HL Tau before ALMA. And then here in the post-ALMA era, TW Hydra was resolved into this beautiful fine-scaled structure, and HL Tau here shown on the right, showing these fine-grained rings. And these were both incredible images. It really took our picture of protoplanetary disks, planet-forming disks, to an entirely new level, and was quickly followed by even larger programs that seem to suggest all of this interesting sculpting and shaping, some of which might be due to planets, or we think at least some is due to planets, seems to be common across the disks we can observe. And so the typical resolution element shown in the bottom left corner is like 5 AU in size. It's very fine grained. So disk science is a very open and active field. There are tons of open questions here, and the point of this slide is to overwhelm you in that we know so little, yet we're asking so many questions and working on so many different aspects of this. Questions like, how long are disks around? What is the typical amount of mass in a protoplanetary disk, and how does that set how many planets can form? What is the meaning of all this ring-like structure? What about the composition of the disk? What are the primary forms that carbon, nitrogen, oxygen take? What are the most important chemical processes that shape the balance of what a planet might inherit or not inherit from its protoplanetary disk? So ALMA is providing a lot of information, but inspiring a lot of new questions clearly. So for me, one of the most useful tools in trying to understand the puzzle of planet formation is by using the chemical structure, the chemistry of these systems as a tool. The way in which this works is that the molecules that are present in space in general, not just in protoplanetary disks, it's extremely sensitive to what the temperature is, the radiation field is. If there's energetic particles like cosmic rays bombarding it, and so it's like a little probe, a little thermometer of your environment where your planets are forming. The molecules themselves can tell you a lot about the local environment they're embedded in, depending on how they shine, what kinds of spectral line patterns ratios they show. You can constrain the properties of the gas, its density, its temperature. And space is itself a very interesting laboratory. It's an interesting way to study new reactions. We can see short-lived intermediates that can basically not be replicated in conditions on Earth. And so while we want to understand the chemical pathways that lead to the formation of habitable planets, in fact, sometimes some of these reactions we actually can never study on Earth and can only study in space based on the low densities and the low temperatures present. So space is an incredibly chemically rich place. Over 200 molecules have been now detected in space. And so here's a table sorted by the number of atoms in the molecules that have been observed. I had to truncate the table and copy it over here just to fit it in here. Now, disks themselves are not quite as, don't have quite as many detections. So here's a table of the number of molecules that have been observed in terms of the different types of molecules that have been observed over time. And so pretty much, we've seen about 13 total molecules, not counting those isotopic versions. But we are starting to see more and more organic molecules. And right here, this inflection point is actually the coming online of ALMA. ALMA has really improved our understanding of organic molecular chemistry in disks. So studying these molecules, it's not just collecting, the newest, funnest molecule that we can possibly find. We want to understand sort of the origins or the fundamentals of that diversity of the observed exoplanets. Why do we have that the diamond planet? Why do we get something like Titan with those hydrocarbon lakes, that nitrogen-rich atmosphere? And so we want to understand where that comes from. And so to ask that question, we actually have to step back even one step further and ask the question, where do the molecules and even the atoms that make up those molecules actually come from? Where does that carbon, nitrogen, oxygen budget come from? And so I can't not quote Carl Sagan when you ask that question, that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, were all made in the interiors of collapsing stars. We are made of star stuff. And I think this is something now that's reached popular culture, that we know that this is, what we have these dying stars to thank for the origins of our elements. And in fact, I personally like this representation here by Jennifer Johnson, showing our periodic table, but now it's color coded by the origins of all these different species. So where did it come from? The Big Bang, hydrogen and helium primarily, or did it come from exploding massive stars in green, dying low mass stars in yellow, or some combination, and they're shaded by a fraction? But the atoms here, while a fascinating picture, it's only actually part of the picture. We need to deliver those atoms in the form of molecules into these planetary systems, or these forming planetary systems. And this is where astrochemistry comes in. So astrochemistry itself, is a field that's only about 100 years old, in that the first molecules ever detected in space were actually detected on our sun. So we had titanium oxide, magnesium hydride. They were seen at the Mount Wilson Observatory, and they were seen primarily in sunspots. So here is an example of a lab spectrum of water, for example, and this is the sunspot penumbra versus the sunspot umbra for comparison. So you can see the lines start to really pick up when you're in the cool region of the umbra compared to the hot surface of the penumbra. And so Molecules were actually first seen in not just interstellar space, but actually on our sun. But now molecules are just common. They're everywhere. Every environment we look, dying stars, in our sun, in interstellar clouds, in comets, in meteorites, everywhere we look, in planets, and so forth. Now, this chemistry of the rich chemistry of interstellar space, it starts its journey on its way to forming planets by originating first in cold molecular clouds. These so-called hole in the heavens, as designated or as called by William Herschel. And so this is Barnard 68, seen in optical light. It looks like there's a hole in the heavens, but indeed it's just a dense cold cloud full of planet-forming potential. So the densities here are lower than a disk, but they're relatively chilly, below 20 Kelvin. Lots of the interstellar light is being blocked, so only about less than 1% gets through. And across this particular nebula, this one only is about 2 solar masses, so it's actually pretty small in what it will form, but they're giant molecular cloud complexes with even more potential. So under these types of conditions, really the types of reactions that occur, so you really only have the time to have sort of 2 different molecules, 2 different atoms come together and react. Otherwise, it's really hard to get 3 species to come together at the densities of space. And so in the cold interstellar gas, here, as an example of a reaction you might think that would happen. So here's an example of an endothermic reaction. Molecular hydrogen's everywhere. There's oxygen, so this would be a natural guess to start with how you might form water. Unfortunately, this has a huge energy barrier to overcome. And so even if you tried to sort of turn up the temperature and cook this cloud and try to make water the hard way, it would take over 5 trillion years to make water via this sort of very simple first approximation of a reaction. But if you add a little bit of extra seasoning to this reaction, if you add a little bit of ionization here and bump into that molecular hydrogen, ionize it and form, through one more step, another hydrogen atom or hydrogen molecule, you'll form H3+ or hydronium. And now this reaction has no barrier, it wants to proceed, and it will lead to the formation of water. And this even can happen at temperatures as low as 10 Kelvin. It takes less than a year to occur, which might sound like a long time, but when molecular clouds are around for millions of years, there's plenty of time to make water in this way. So where did that little ionization kick come from in the first place? For me, this is one of the most interesting things. The same dying stars that, the stars that sort of were populating or polluting our periodic table with all of that interesting atomic goodness. Here, this should actually play, maybe it'll work. This is a simulation of one of those dying stars ejecting carbon, and there's iron into the interstellar medium. That's density, that's temperature. These stars are enriching our interstellar medium when they explode. But they also, in the process of exploding, they also can accelerate energetic particles, so-called cosmic rays, the very things that can actually kickstart that chemistry and ionize that first step, that molecular hydrogen. So dying stars, we have a lot to owe to them. They are not only seeding the material, but they're also powering the chemistry that leads to the formation of things like water and organics. So going from now this chemically rich cloud down to the planet-forming environment, disks themselves are highly chemically structured. So if you look at a disk cutaway here, you have temperature gradients both from the surface down into the cold core. There's a hot surface or the hot inner disk into the cold core. These dusty disks will also manage or filter the light that can pass through it, which changes the temperature and the radiation field that can actually reach the cold core, the cold planet forming environment. And so this will naturally set up sort of a structure where you have an ionized surface, but molecules can survive, and you have an icy core and icy midplane deep within. And so depending on sort of where your planet's forming, you might have different ice compositions or different gas atmospheres. And so we call this sort of transition point when a molecule goes from being gas to ice, we call this a snow line. And so in a cartoon sense here, a snow line would just mean you have bare dust grains, in this case, water vapor, and then on the outside of the snow line, you have ice-coated solids. And so this would lead to, in this, if your planet formed at a distance or closer to the star, you might end up with an ice poor core, and then whatever is remaining here in the gas would fill your envelope. And out here, if you form, you have an ice-rich core as an example, and maybe a volatile core envelope, for example. So this is just one possibility. And so you can get different compositions, there we go, depending on where your planet forms, if it's interior to that water snow line, or if it's interior to something, a snow line of something completely different. And so this led to some cool results where if you sort of paint on some typical water, CO2, CO abundances that we know about from molecular clouds, you can create graphs of where you would expect the composition of the planets that form to radically shift as you cross over those snow lines. And this was a really neat way of describing it through this carbon over oxygen ratio I mentioned earlier, where depending on the location a planet forms, you'll have different compositions in the gas versus the ice, whether you're near the water, CO2 or CO snow line. And so this was really exciting because we thought, hey, maybe if we can measure that carbon over oxygen ratio in those exoplanets, we can link it to the place in the disk they originally formed. Now, this was really cool. This idea was really cool. So this is sort of a theoretical picture here. And, you know, this would result in maybe some regular patterns of planet composition. But in reality, it's always more complicated. Chemistry can evolve heavily over the course of the lifetime of the disk. You can have mixing between different environments. Ices can be transported throughout. And so really the necessary thing to try and understand what the range of compositions planets can inherit from their disk and what they can possibly, you know, what they could possibly look like requires measurements. And so we have so many windows into planet forming disks. So, you know, we have both in the inner hot regions, there's hot molecular lines seen in the near and mid infrared. ALMA is probing this green region, this colder region. The core is this sort of icy component. The scattered light will come off the surface like what we saw with Hubble. And so you have a whole bunch of different reservoirs we can probe with different molecules, different wavelengths of light, and piece this puzzle together. And so ALMA gave us some really amazing, or ALMA is still giving us some really amazing pictures of the different molecules and where they're present. This is just a gallery of a few examples of different molecules and their distributions in different disks. A neat thing about this graph to me is that this, and this, like sort of these four images all are the same system. And so you have in the same system molecules that have different patterns. So this is telling us chemistry is varying with distance from the star. This protoplanetary disk would form different planets depending on where they form. So we can see this in action. Now, let's see. I'm gonna skip a little bit ahead here and say, there we go. All right, so when we get data like that, we can't just, you know, take a picture and say it's the end of the day. We can take what we do is we take the intensity and we'll either make some assumptions and say, hey, the intensity of the line is related to roughly how much there is, and it's some function of its temperature, and so we can approximately estimate how much, in this case, 13 CO there is in the disk. An alternative way that what my group works on is forward modeling, where we try to construct a realistic picture of where 13 CO should live, and we create synthetic images which we compare to data. And as we constantly adapt and improve our models until we can match what we see on the sky. And the beauty of that is it tells us what reactions matter, it tells us what the physical drivers of the chemistry are, and so forth. But models are really hard. They're really complicated. And so head exploding emoji down here is not intentional. You have to assume a lot or constrain a lot about your source, ideally get observational constraints. Then you have to bombard it with radiation. You have to assume something about the chemical reactions that can occur, and this is something we're constantly working on. From this, we make synthetic observations and then rinse and repeat. And so from this, you know, there's many different ways you can approach computational work, computational astrochemistry. For the simple molecules where the chemistry is just understood already, we can use those simple molecules as little canaries in the coal mine to constrain what the irradiation level is, or how much energetic bombardment there is, and so forth. So this really lets us put our physical understanding of planet formation to the test by using simple molecules. More complex molecules that may have poorly understood chemistry, we can use those to understand, like, if we're missing different types of reactions. Are they forming mainly in the gas or in the ice phase, or maybe some combination of the two? And so this lets us start to actually test the chemical pathways and if we're getting those right. The neat thing about disks is that they take, conventional knowledge of astrochemistry and sometimes throw it out the window. And one amazing way is, that these disks, as they form planets, they're actually changing their own local composition. And so the future planets that form might not look anything like the first generation of planets. And this is because when those solid tiny dust particles evolve over time, they'll grow, they'll gravitationally settle, and they'll start to drift inward. And so you can end up redistributing icy coated grains completely differently in the disk, depending on where you are and what time you're looking. So it's a fascinating window into how planetary chemistry can change over time. And our observational windows are different. So ALMA, that I've told you about so far, is really good at probing the vertical surface, the observable gas-rich surface. An exciting thing that will be coming up in the near future is the James Webb Space Telescope that will be launching later this year. And the neat thing about it is that it has the capability of detecting the icy reservoir through mid-infrared ice feature, or near and mid-infrared ice features. And so we should get a complete picture through combined ALMA and JWST observations, especially for disks where they're in these sort of favorable inclinations, where we can see the ice reservoir better. So a couple of neat connection points I just want to highlight before wrapping up is that we have some out of ALMA, so there have been some really interesting developments in the last 5 years, namely that there have been certain molecules peaking up that we never expected. Small hydrocarbons are extremely bright, extremely abundant. These molecules are well known, actually from the dying star community, the AGV star community, that they are extremely sensitive to carbon over oxygen ratios, especially in the gas. And so by measuring their brightness or their quantity, we can start to get a handle of the carbon to oxygen ratio in the gas that that planets can accrete. And the neat thing about this is connecting it back here to HR 8799. This particular disk that I showed you here, this is a nearby protoplanetary disk, TW Hydra, that has this hydrocarbon ring. It matches up really well with the same pattern of carbon over oxygen ratios in the exoplanetary system, HR 8799. This could be total coincidence. In fact, if you look at other disks, they have different ring-like patterns, and that's actually shown here. So hydrocarbons sometimes are more peaked, sometimes they're double ringed, and sometimes they look like TW Hydra. But maybe this is a way in which we could time planet formation potentially in the future, or at least see what the variety of carbon over oxygen atmospheres are possible. Another really neat way that we can connect exoplanets and the potential for habitable planet formation to disks is via these future JWST observations that we're looking forward to. And here I'm just highlighting some neat work that my postdocs, Dr. Nick Valerie and Dr. Dana Anderson, are working on to create synthetic detailed icy spectra of what we should see from a realistic protoplanetary disk viewed from the side in this case. And so depending on what slice you look at, which layer on the disk you look at, you see different ice species peak up because the composition is varying spatially across the disk. So these are the most detailed ice models made to date of a protoplanetary disk. Another neat area that we're exploring right now is that we want to localize where the ice presently is. I alluded to the fact that the ice grains are growing, evolving, and moving. This can be changed depending on when you look, so it might be more mixed, it might be more concentrated, but if you happen to have something like a ring or a gap blocking the flow of ice inward to the star, then maybe you have ices locked up in the outer disk that can't actually make their way into the inner, perhaps terrestrial planet forming region. And so understanding where the ice is an exciting topic, and we were awarded time with the James Webb Space Telescope in cycle 1. So we found out just a few weeks ago that we were able to map ice, or we're planning to map ice in the V4046 Sagittarius system another famous disk system. This one is particularly fascinating, at least to me, because it's really close by, but at the same time, it's the background of this particular disk aligns with a whole lot of background stars. You can see here, all those little dots, those aren't artifacts, those are all little distant stars that I've circled now here for you. And there's over 40 background stars behind this disk that let us pierce through and measure the total amount of ice between the star and us, and sort of map out the ice across the face of this disk. And the other neat thing about this data is that we're using the coronography mode on James Webb. And so not only will we get these lines of sight going through the disk and getting the ice along the full depth, we'll also get reflected ice features from the surface via the coronagraph. All right, so with that, I wanted to give you a couple of highlights and also just like let you know about where we are in protoplanetary disk science these days and what problems that are keeping us up at night. Really, we're motivated or excited by all of the last few decades of the characterization of exoplanets and how much we've learned about exoplanets, their diversity, their orbital architectures, their compositions, but also the puzzles within our own solar system. The fact that, where is the water in Jupiter? Where did the water on Earth come from? And the carbon, where did it go? So over the last decade, there have been significant improvements in the observational picture we have of protoplanetary disks, as well as the modeling. We're learning so much about the physical environment and how this sort of icy transport actually seems to be a pretty crucial part of the puzzle in understanding what happens for future planets. Along those lines, we're seeing that the physical environment and the chemistry is extremely well coupled. And so this transport of ice seems to be key and has big implications for carbon over oxygen ratios in these newly forming planets. So this will soon be testable with James Webb, actually not only for protoplanetary disks, but also in the atmospheres of close-in gas giants as well. So stay tuned there. And also I want to just point out that a lot of what we've learned about protoplanetary disks is from objects which we know the names of. But the vast majority of systems, the typical systems that might form something probably closer to our solar system, it's relatively poorly known. So we need to go to statistics. We need to go get demographics of the planet forming potential for these disks. What is a typical carbon over oxygen ratio? What is the typical amount of mass you have to form a planet? We don't know these answers to these questions yet, but we can over the next decade. And so this will be an exciting decade coming up to start to actually compare to the demographics of known exoplanets, as well as put our solar system into context. And I want to just take a second and thank my wonderful research group. So pictured here, I'm extremely lucky to have such a wonderful team behind me doing this beautiful science. We all really, everybody collectively misses the normal times when we could observe or present our science or give public talks. Here is my student Abby, as well as like make Christmas cookies themed with the protoplanetary rings I showed you earlier. Those were the good old days. But I'm so wonderfully surprised every day with my group and how resilient they've been. And then here is a picture of we do these regular events to check in with each other, social events, and this was us making like spring themed origami. So they put up with my shenanigans and are doing wonderful science at the same time. So I'm extremely grateful to them. So I thank them very much, and I thank you for your attention. I'm happy to take any questions you have.
So if you have questions, we have a Q&A that you can type them into, and we'll relay those to our speaker. Thank you, Dr. Cleaves, for a great talk. Do you want to just look over the questions? Can you see them, or you want me to read them?
I actually can't see them, but I could close the
no, let me. So I'll just read you some. So, is our solar system layout and composition unique among the exosolar systems you have studied, or are we in line with the others?
So it's a great question. Oh, I'm kind of hearing an echo. Is that on my end? Okay. So the answer to that is that we're still trying. We still don't yet fully know, but We do lie in a part of parameter space, our solar system. When you compare it to all the known detections of exoplanets, we do seem to be relatively more extended and have gas giants on relatively distant orbits, or Earth's on a relatively distant orbit. But mainly the reason for that is that there are selection biases. I wish I actually had a graph of this. I'm trying to describe it with my hands, and it's really hard. There are selection biases to finding planets that are more massive and closer to their star. And so I think that we're in a point where we don't quite know how typical we are, but when you correct for the unknowns, the biases in the samples we have, it seems like on the whole, we have it seems to be fairly typical, although the most common type of exoplanet, which is it's a super Earth or sub Neptune, depending on, like, I guess, glass half full, half empty. We don't seem to have a planet of that class, and that's the most common type of planet that we have found so far in the exoplanet catalog. So we're missing that, but at the same time, it seems like perhaps we're not that distinct. Our architecture is not that distinct. The compact planets I showed at the beginning, only about 10% of our known exoplanet systems are in that really compact configuration. 90% are more extended like us. But again, we're kind of missing some of the key players in our solar system, at least today. I mean, maybe they were there earlier, but at least today.
And you'll have to unmute.
Okay, gotcha. The what caused the jump in the mid-90s in the plot of the submillimeter molecule detections?
That's a really good question. So there was a dedicated survey of Enceladus right there. Like that was entirely like one massive effort. A lot of telescope time was dedicated to finding new molecules. And so, yeah, those major leaps require really big commitments from observatories. And so that was a really big commitment. And so, we're now with ALMA, we've had this ALMA telescope now for a decade, and we're reaching a point where where the competition is still extremely high, but we're able to sort of go after these risky, deeper observations, looking for new molecules. There's new techniques out there for trying to find very faint molecules that we don't even see in our data or aren't even looking for. And so there's some neat data type techniques, data analysis type techniques. And we're just at a point where it's like we can start to actually explore these unknowns, chemically speaking. Whereas before, in the early days of ALMA, it was much more difficult to go hunting for something new. I don't know if that was the answer to the question, though.
Is there anything especially surprising in the list of molecules that have been detected so far? What are the most interesting or complex or surprising detections?
So there's the lack of there's a couple of things. So the fact that early on, the surfaces of disks looked very water poor, water dry, not just because of freeze out, but the grains themselves looked bare. Now we understand it's because the chemistry really is connected to the evolution of those tiny little dust grains as they're growing and evolving and moving. So the surface is sort of drying out over time. Other really cool things, let's see. So organics, I mentioned organics, those have been a big contribution, or detections of those have been a big contribution from ALMA. And for example, methyl cyanide, CH3CN, happened to be the first complex organic seen in a protoplanetary disk. If ignoring pause for a moment, but for a simple molecule, CH3CN, that was the first organic molecule seen, even though methanol was the one everyone was hunting for. And so the ratio between those was about 1-to-1. When in interstellar clouds, it was 1% methyl cyanide to methanol. And so there is something bizarre going on with the organics. It's likely tied to the water and likely tied to something has to do with the drying out of the surface via the water ice getting sequestered to forming larger bodies. Methanols probably go in the same way. Methyl cyanide might be forming more actively. I mean, we don't totally understand, but we're getting weird organic ratios, a lack of water, and actually mentioning PAWs, you know, for some reason, the PAW emission, which is so bright in the interstellar medium, is not there in protoplanetary disks. Is it because it's grown to larger sizes and we can't observe it because it's formed a solid phase? Or was it destroyed by the radiation field from the star early on? Those are things that actually, that latter question, JWST will shed light on.
What is the typical distance of the protoplanetary disks that have been studied so far from Earth? I don't know if they mean distance like size.
Yeah. Distance, they're roughly 140 parsec away. So, you know, we're talking like 500, 600-ish light years away. So yeah, they're not in our backyard, sadly. They're pretty far away. The closest one, TW Hydra, is 60 parsec away, and that's and that seems to be, I don't think we found anything closer than that. So no, sadly, we're like not, these are not in our backyard. I mean, exoplanets are definitely in our backyard. There are exoplanets around around nearby stars, primarily the low mass stars, the M dwarf stars around us. So we know that planet formation has occurred in the past, but the systems we're studying now, the regions of recent star formation are pretty far away.
What does the carbon and oxygen abundance we have at Earth tell you about the disk evolution of our own solar system?
What is the carbon, the C over O ratio?
Yeah.
Yeah. So going back to that initial, you know, plot of sort of the carbon and nitrogen abundances. I mean, we know that from our early solar system, something happened to Earth's carbon. I mean, even the asteroids were pretty carbon poor, and so we know that there were some major events that sort of devolatilized, removed carbon from the rocky component even before Earth formed, and then something after Earth formed kept it going. And so we know that that's a process that's actually a pretty hard process to probe directly via observations, because it's the inner disk and the inner midplane. It's one of the hardest parts of the disk to actually observe, even JWST. So it's in the infrared wavelength light. We really see mostly the surface, and we have to sort of infer what's beneath. It's like an iceberg where you just see the tip and not the bulk. And so the inner disk, that hot inner disk region, is going to be is pretty hard to probe. But the ideas out there now is we probably had maybe some early outbursts that heated up the inner disk and converted a lot of the refractory forms of carbon into some more volatile forms that couldn't be trapped. And so that's a hypothesis. And now with disks that are being observed, like VA83 Ori is a currently outbursting disk. It's been recently surveyed with its molecular emission, and you can even see like the transition from water going from gas to ice. You can see a ring of organic molecules being pushed out. And so it's a really neat way to see this from different perspectives, although it's not the same system. Instead, you have to sort of look at the population of disks out there and sort of try and piece together how we fit in. But we think it's probably has to do with early outbursts, shaping the carbon over oxygen ratio, to clarify.
What causes the formation of a rocky planet instead of a gas giant, or vice versa?
So the story we tell, you know, in our intro astronomy classes is that the rocky planets likely had less of a solid reservoir. So they probably formed pretty close to the star where there was very little ice. And then we, you know, then continue the story and say, well, beyond some radius where there's now more ice, more water ice, there's more solids. And you can form larger and larger cores. At some point you reach a size where, you know, roughly 10 Earth masses, you have so much mass that you start to like hold on to the nebula itself and accrete the gas gravitationally and capture it into your envelope. And so that's what we say. I mean, we still think that's probably what's happening. But at the same time, we are seeing large planets orbiting very close to their central star, well interior to where there should have been any ice. And so the question is, did they migrate or did they form in situ? And there's arguments for both, that they formed further out and moved inward, or that they instead formed locally. And we should, by getting statistics on those planets' atmospheres, we should kind of be able to see it imprinted actually in their carbon over-oxygen ratio, bringing it back to that. So hopefully that'll be answered soon as we get more statistics on that key parameter.
There's a lot of bias in exoplanetary systems. We observe towards hot, fast, heavy objects as opposed to cold stuff in the outer solar system. Can disks help us predict what we should be seeing in the outer solar systems of, say, hot Jupiter systems or compact systems?
I think so. And so in the disks, we're preferentially looking at the outer regions. We actually are better tuned to seeing things outside of solar system scales, outside of 1020 AU, and our solar system gives us the picture of sort of what's going on inside of that radius. And if you look at the patterns of rings, they do tend to be much further apart, further out than our own planets. And so maybe there's some hints of migration in action where if you sort of push the distribution of rings inward radially, it starts to match up with the distribution of exoplanets. And so maybe there's some like tentative signs of migration in action there. But it does offer a complementary perspective. I think that, for a solar system, we don't have no data out there. We have, the comets and their ice-rich compositions, and those will be directly comparable with those sort of ice experiments with JWST. So we'll be able to sort of see if there's commonality there. Yeah, I don't know if that answered the question. I think that I'm trying to remember it. Oh, it was like, can we use disks to complement it? I think there are other ways to figure out what's going on in the outer disk. Sorry, the outer exoplanet population. There's also microlensing as another cool avenue to find exoplanets very far from their star. But it's very complementary indeed to what we can study with disks, which is much further out.
Besides JWST, is there significant potential with any of the new super large ground-based telescopes, TMT, ELT, for instance?
Yeah, the new class of extremely large telescopes that are either being planned or are underway. I mean, the ground-based, I don't even think I showed any of this data. Like even the telescopes we have now, especially VLT Sphere, have made gorgeous images of the scattered light surface of protoplanetary disks. And in some cases have found companions. PDS-70 is a wonderful example of a system. You just like Google PDS-70, I promise it will come up. It's a ring, and inside of the ring, there's a luminous companion and maybe a second luminous companion. And they have hydrogen alpha emission associated with them, which is suggestive that the material is crashing onto those planets. And so with the new generation of telescopes, we won't have a handful, or we'll have more examples of that, especially as you get to sort of more sensitive telescopes, which lets us look further away, but also getting to smaller inner working angles on coronagraphs, so you can start to look for planets closer in. So I mean, the possibilities of finding companions are really exciting, and also the possibilities of just what do the substructures look like? All those beautiful ulna rings and gaps, are they there in the tiny grains too? Are they not? It's not always, for the cases where we know, it seems like they're different. The patterns are different. And so we're trying to understand what that means.
Haven't one or two amino acids been found in the interstellar medium or molecular clouds? Have any been found in protoplanetary disks?
No, none in protoplanetary disks, but indeed in meteorites, amino acids have definitely been found And so, you know, there's a lot of work going on to understand when those amino acids originally formed. And there are interesting properties of these amino acids. They can take, you know, different mirror forms or handedness. And so, you know, on Earth, life seems to have sort of the same pattern, the same mirror symmetry across all life on Earth. And so, when did this get started? I mean, there's really fascinating stuff going on out there. Sadly, with disks, the most complex molecule we've seen really is methanol and methyl cyanide. Nothing yet more complex. We would need more ALMA, more dishes, not larger dishes like spread out in a larger area, but we just need a higher density of dishes so that we could collect more light to find more rare species. But I mean, amino acids would be hard regardless, because those types of molecules, to observe them in distant space, they're so floppy, and they don't have strong individual transitions. Spectroscopic transitions.
Can studying planetary rings in our own solar system tell us anything about protoplanetary disks?
Is that, are you referring to the like the belts, like the asteroid belt, the Kuiper belt?
So I think I think maybe they meant planetary rings, but go either way with it, okay?
Definitely. So for planetary rings, yeah, you have the interactions of the shepherding of moons, you know, for the rings of Saturn, of Uranus. And so, I mean, that's what's sculpting many of the rings that I showed you. There have been so many theories out there trying to explain what could cause the patterns in the rings, and pretty much the vast majority, you know, they're slowly getting knocked down, and planets is still reigning. So we know that at least, or we think that at least some of those rings are planets that are sculpting out their paths along their orbits in the same way the moons are shepherding the rings of Saturn. And so yeah, so we can learn a lot. I mean, gas giants are like miniature solar systems. We think that the ring system itself is not a remnant of like a moon forming disk, but we do think the gas giants were surrounded by disks, their own circumplanetary disks. And out of those, the moons themselves coagulated. And there's a lot of interesting questions around circumplanetary disks, because so many of the moons are icy, and yet our physical understanding of those disks points to them being so deep or so close to their so deep within the planet's gravitational well that they should be really hot. And so it's a little confusing as to where they got all of that ice. A lot of open questions on circumplanetary disks. But an exciting thing there is that ALMA, people are looking for a circumplanetary disk dust with ALMA, and you know, one of the planned upgrades for the VLA, the next generation VLA is also suited to trying to find those like resolve the pebble disks around planets, the moon forming disks.
So a question about you. When most people think of astronomy, they don't think of chemistry. So how did you get interested in astronomy in the first place? And then what specifically drew you to studying astrochemistry?
Since I was young, like fifth grader, I you know, loved astronomy and found out it could be a career. And so I sort of ran with it throughout my education, through high school. One of my science teachers loaned me their astronomy textbook from college when they were in college. And so like it definitely was always my passion. But I also loved other things. I loved building things. And so I wasn't actually sure if I would become an astronomer or an architect, but I decided in the end, you know, I should probably, you know, learn the basic of physics either way. You know, building should probably stand, right? And so I ended up going towards the path of astronomy. And while I was an undergraduate, I found that I kept gravitating, no pun intended, gravitating towards papers about newly forming planets. And that's what helped me zero in personally on why being interested in the formation environment of new planets. And I personally love that it's like a field of potential. It's you study these systems to try and understand what possible planets can form. And so it gives you, there's a lot of room for creativity in this field. Molecules themselves, or the chemistry of these systems. I wasn't formally, personally trained in chemistry itself, but a lot of the chemistry we're studying is in fact physics at its core. It's physical chemistry. And so, yeah, studying these systems, you know, you can treat your molecules as interacting partners and their reactions, the probabilities. There's a lot of statistics in there. Are they gonna, you know, tend to form something like methanol? Are they gonna fragment to pieces? And so there's a lot of math and physics baked in. And so I really like that perspective that the chemistry and the math and the physics and the astronomy all come together and give us this really fun, multifaceted view. So it was a long path, but you know, it's an incredible field to be working in. I think, you know, protoplanetary disk science, it is rapidly growing, you know, puts it so lightly. Every single day, almost, last I calculated, over the last 5 years on average, I calculated that nearly 2 papers came out. 2 refereed papers came out every single day on protoplanetary disks. So the literature is just impossible to keep up with. It's such a rapidly growing field right now. I feel bad for my graduate students trying to keep up with everything going on in the world. And like also the historical literature, everything on top of that. But yeah, that was my general path to getting here. But it's not the only path. You know, my students have very different backgrounds. My postdoc have very different backgrounds. And I love fostering a group that's just, that comes from so many different perspectives.
So I think we've actually exhausted the questions in the Q&A. So unless one pops in just now, I think we can thank you again and wish you much success in your work going forward. Thanks so much for being our speaker tonight.
Thank you everyone for joining. All right.